Okay, so I just wanted to recap what we had talked about as far as this topic of intermolecular forces. Okay, so first of all, remember what we're talking about here. When we've been talking about covalent bonding, we've been talking about things that have held atoms within molecules together. All right, this is going to be a topic where we're going to talk about what might cause neighboring molecules to either stick together or to not stick together. All right, that's going to be an intermolecular force. All right, so there's a couple of different types of these forces, and the first and probably easiest to understand is what's called a dipole or a dipole-dipole interaction, because it actually requires two dipole molecules. All right, so first of all, a little reminder about what a dipole molecule is. It's a molecule that has an overall slightly positive and slightly negative side to it, all right? And it's caused by the presence of a polar bond, all right? Or at least one polar bond. So I've given the electronegativities of both hydrogen and chlorine here, and so if we had this molecule right here, you can see, well, chlorine would have an electronegativity of 3.0, hydrogen would be 2.1, and that would make this a polar bond, meaning chlorine kind of hogs the electrons that are in this bond, pulling it towards itself. All right, that's going to create a slightly delta negative or slightly negative side and a slightly positive side. The delta negative is the side that has the electrons pulled towards it. Okay, well, the thing is, if you got these molecules, they're not just going to have one of them. There's going to be neighbors. All right, so if I draw one of the neighbors right here, you would have the same situation. This side right here would be slightly delta positive because these electrons are being pulled towards the chlorine, and that's going to be slightly negative. All right, so what's going to end up happening is that there's going to end up being a slight attraction between the slightly negative end of this molecule with the slightly positive end of this molecule right here, and that's what we call a dipole-dipole interaction. All right. So, the reason that's important is that it causes these molecules to have a slight amount of stickiness with each other, and that's going to have a major effect on things such as melting points and boiling points. If things have a reason to stick to their neighbors, they're going to tend to be more towards the liquid and solid end, whereas if things don't have a reason to stick to their neighbors, they can separate from each other and are more likely to exist as a gas. Okay, so the next type of interaction is actually a type of dipole interaction, and it's called a hydrogen bond. All right, this is the most common type. It's a very common type of dipole interaction, and you're going to see this in lots of molecules. All right, what a hydrogen bond is, the name is a little bit misleading because when you hear bond, you think covalent bond. It's actually, sometimes I call it a hydrogen stickiness because it's a force that causes an attraction between molecules, but it's not an actual covalent bond. All right, so first of all, what causes one? So a hydrogen bond is an attraction between a lone pair on either a nitrogen, oxygen, or fluorine atom with a close by neighboring hydrogen which is connected to a nitrogen, oxygen, or fluorine. All right, and I know that that's kind of a mouthful, and I'm going to kind of go through it step by step here. But whenever we have a hydrogen bond, we typically represent that with a dotted line in the area that you would have that stickiness between the molecules. All right, so I've kind of laid out here the requirements for a hydrogen bond. First of all, you have to have a lone pair on, and I'm going to call it NOF. All right, that means a nitrogen, oxygen, or fluorine. All right, so what's special about these atoms? If you look at the electronegativity charts, these are the ones that are very electronegative. All right, let's take a look over here. We've got a water molecule right here, and we've got another water molecule right here. All right, so this right here, this is an oxygen, obviously, and because it's an oxygen, it's going to have some lone pairs. So there is a lone pair on an oxygen. All right, so that satisfies this first requirement, that there's a lone pair on a nitrogen, oxygen, or fluorine. All right, And then over here we have a hydrogen which is connected, which is bonded to an nitrogen, oxygen, or fluorine, in this case oxygen. All right, so that satisfies this third requirement. And the second requirement is something that sometimes we forget. It's got to be near. They've got to be near each other. All right, because if this water molecule were way far away, it wouldn't have feel that same effect. It's a little bit like saying, you can make the analogy to how magnets stick together. You have to have the south end of one magnet near the north end of another magnet. If you can't say all of those things, things won't stick to each other. All right. Obviously, if you have two magnets, but they're separated by a very long distance, there's not going to be that attraction. All right. One thing that's important about these is that molecules that contain hydrogen bonds tend to have higher melting points and boiling points than molecules that can't hydrogen bond. All right, and that's because they have a reason to stick to each other, which is going to mean it's going to require more energy and higher temperatures to cause them to separate from each other. All right, so why do we get these hydrogen bonds? All right, well, remember, oxygen is going to have an electronegativity of 3.5, hydrogen's 2.1. So what that's going to mean is that in this water molecule, I could draw a slightly negative charge right here and a slightly positive charge right here from these electrons being pulled towards the oxygen. And on this neighboring oxygen, water molecule, I could do the same thing. All right. So what a hydrogen bond is the attraction between the lone pair on this delta negative oxygen, which means it's going to have what's called a high electron density, all right, with the delta positive part on this hydrogen right here, all right, and this lone pair is going to really like the delta positive charge on that hydrogen. And again, the way we represent the hydrogen bond is with a dotted line that looks like this. So whenever you see a dotted line between molecules, that generally means a hydrogen bond is existing in that little area. All right. So one thing about hydrogen bonds that makes them very important. First of all, what is the most important place we ever see hydrogen bonds? It's going to be between water molecules. All right. Water is an extremely important substance. And if it were not for water's ability to hydrogen bond, it would actually be a gas. All right, it's a very small molecules, and small molecules of this side generally tend to be gases. The only thing that lets it be a liquid is that there's this stickiness between the molecules because of the hydrogen bonding ability. All right, so hydrogen bonds are also very important in biological molecules such as protein and DNA because they provide little areas of stickiness that allow them to function properly. All right. Another thing is that even though we generally talk about hydrogen bonds as being forces between neighboring molecules, I want to point out that if a molecule is large enough, you can actually have a hydrogen bond within the same molecule. All right. And you would call this, instead of an intermolecular bond, you'd call it an intramolecular bond. So a classic example would be something like this right here. All right, this has got 1, 2, 3 carbons, and you've got these OH bonds at the end of it. But notice this part right here would satisfy the lone pair on the nitrogen, oxygen, or fluorine. And this right here is a hydrogen connected to a nitrogen, oxygen, or fluorine. So what that means is that you could have a hydrogen bond between this oxygen and this hydrogen, even though they're within the same molecule. All right. Keep in mind it has to have a decent enough size to it to allow this type of thing to happen. But you'll see you'll see that that does happen in especially in proteins. All right. So let's see, one thing that I mentioned is that you see these a lot in DNA. So I want to return to something that y'all probably had in biology, which is the structure of DNA. All right. Back in biology, you probably represented DNA as A is connected to C, is connected to G, is connected to T. And then we knew that A likes to stick to T, We know like C likes to stick to the G, which is on the neighboring strand. G likes to stick to C, and T likes to stick to A. All right. Well, remember when we did this? Within this strand of DNA, all of these things are covalently bound to each other. All right, but in all these things are covalently bound to each other in this strand right here. But between strands, notice we never talked about there being a covalent bond, and that's because the thing that holds the strands of DNA together is hydrogen bonding. All right, so this little part right here is adenine, all right, which we generally would call A. This right here is thymine, all right, and what allows them to stick to each other is if you look at adenine, there's a hydrogen connected to a nitrogen right here, which is right across from an oxygen, all right, and so that right there would allow for a hydrogen bond to exist. Here you've got a nitrogen near a hydrogen on a nitrogen. That again is also a hydrogen bond. And notice that the shape of this molecule allows two of these to exist. And two of these existing is stronger than just one of them existing. All right. This right here would be a cytosine. This would be a guanine. And notice that there's actually 3 hydrogen bonds that can exist between those molecules. All right. And so what it was that actually allowed caused an adenine to be particularly sticky with a thymine is the shapes of these things. It puts the delta positives on one molecule directly across from the delta negatives of another. All right, and if you have enough of these little areas of stickiness, that caused the entire strand over here to want to stick to the entire strand over here. All right. One thing that an analogy that you can make with hydrogen bonds is that they're like the Velcro of molecules. All right. And if you think about how Velcro works, it's not as strong as concrete. All right. These bonds are not as strong as regular covalent bonds. But one nice thing about Velcro is that you can rip it apart and then you can reattach it. All right. So if you remember, whenever DNA likes to needs to make a copy of itself, these strands had to be able to separate from themselves. All right. And if you think about it, if these things were covalently bound to each other, there would be no way for them to easily separate. All right. So, but because they're kind of lightly attached to each other, more like Velcro, they can the bonds or the attraction is weak enough so that they can be pulled apart whenever they need to replicate. And then when the new strand gets formed, just like Velcro can reform the bond, it's going to create another reform that area of stickiness.